Well, welcome to this second lecture in the geometry series. I hope we've overcome our slight technical setting up problems. And I see the time is really 1 o'clock, not 2 o'clock. Don't be alarmed. Well, this talk is a little different in style and perhaps in difficulty to the first one, which was about pictures in mathematics and the history of mathematics. And today I want to talk about a rather ancient and unusual aspect of mathematics and numbers, which goes by the name of continued fractions. Just yesterday I was looking on the web and I came across this headline story from I think it must be a Canadian or an American small-town newspaper called Prairie Life. And as you can see, it's really self-authenticating. We're used to representing numbers in particular ways just as fractions, or as mathematicians call them, rational numbers, where a rational is defined to be the ratio of one whole number divided by another non-zero whole number. And sometimes we use decimals. So, for example, pi, 3.141592. If we were to represent that more formally, what we're doing really is expanding pi in a series of terms where we multiply some number, first of all, by 1 plus another number times a tenth plus another number times a hundredth, and so on, indefinitely. And we can just keep those coefficients here, the A1, the A2, the A3, and we could write them in a list in this way. And in this case, pi is a so-called irrational number. Its decimal expansion goes on forever. And we would be codifying and representing pi by this infinite string of digits. Rather more of them are shown in this cartoon representation of the decimal expansion of pi. Decimal expansion of pi is one of those things that you read about in Dan Brown novels. Everyone suspects there's some deep and perhaps even sinister structure to it. And if only we can unlock it, the secret of the universe would unfold in front of us. In fact, Carl Sagan once sent me a copy of his science fiction novel Contact, which was made into a movie, because he saw I'd written a book called Pie in the Sky, and he said, read this story and you'll learn something new about pi. And you remember what the plot was of the movie Contact, or the novel, that when civilizations become sufficiently advanced that their computer power allows them to explore fantastically far downstream in the digits of the expansion of pi, there's an important message waiting for them there about technology and their future and existence. But only when you're sufficiently clever, both technologically and perhaps in other ways, will you be able to reach that downstream part of the expansion and learn the secret of the universe. But nonetheless, decimals are not entirely satisfactory, because we know that having a decimal that never ends doesn't even distinguish for us between rational numbers and irrational numbers. So a rational number like 1/3 has a decimal expansion 0.333 recurring forever that doesn't end. So we can't even capture that distinction. And a pedant might say, well, why are you choosing the base 10? The technical expert here before the lecture began came and showed me his watch, which it didn't seem to me a very useful watch. It's a binary watch, or it's a digital watch, but it's in binary. So you could, if you wish, change the base of the decimal expansion. Which one should you choose? We choose 10, of course, because in ancient times counting systems evolved to match the fact that we have 10 digits on our hands. And finger counting was the origin of most sophisticated counting systems on Earth. There's one interesting one that you come across in Middle America where the base is 8. And what's going on there? People are counting the gaps between the fingers rather than the fingers themselves. Well, there's a different way of writing numbers that mathematicians like, because it turns out that this way of representing numbers unveils a lot of the deep and hidden structure that decimals miss, and also distinguishes between irrational and rational numbers in a very clear and interesting way. Suppose we start with a simple quadratic equation like this. Then we can rearrange this equation. If we just divide by x, then x minus b minus 1 over x would be 0. So shift these two over the other side, and we're saying that x is b plus 1 over x. B is just some number, so it might be any number you like. Well, what we could do here could be to proceed rather incestuously. We could take our formula for x, b plus 1 over x, and substitute it for x over there. So x will be b plus 1 over b plus 1 over x. And then we could do the same again. We could substitute for that x there using this formula or the whole of this formula, and do that again and again and again and again. And what would result would be this typesetter's nightmare here, that you'll see we'll change notation in a moment, that x looks like b plus 1 over 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 b, and so on forever. We can put any formula we like for b there, but if we go back to the quadratic equation there, we know how to solve that, or at least, when we were at school we used to know how to solve it. And x is minus minus b, so it's b plus the square root of b squared plus 4 over 2. So if you put b as 1 here and here, x is 1 plus the square root of 5 over 2. And that's a famous number, so-called golden ratio. And it's about 1.618 and so on forever. And so you see what we've done here, if we put b as 1, this continued fraction, as we're going to call it, 1 plus 1 over 1 plus 1 over 1 plus 1 over 1, so all ones down this staircase. This is another way of expressing this famous number, 1 plus the square root of 5 over 2. So this is really the paradigm for this type of representation of numbers as a continued fraction. Well, this horrible notation was introduced rather later than the very idea of writing numbers in this type of expansion by rather elegant-looking William Bruckner, who was one of the founding fellows of the Royal Society and, in fact, was its first president. So William Bruckner was a Viscount. He did a lot of work in mathematics and series and was the first person who introduced this way of representing fractions. The fractions he were interested in was, here's an extract from his original paper here. So this was the number he was trying to represent. In this case it was 4 over pi. And he wrote it in this rather unusual way. It's a slightly different continued fraction to the one we represented. What he was doing there was seizing on some work by John Wallis, who was almost a contemporary, another founding fellow of the Royal Society. You probably know him as one of the first serious students of cryptography in England, who had the curious distinction of being the cryptographer for both sides during the English Civil War. So you can see why he was so successful. And he had devised this rather pretty and powerful infinite product formula. So a way of writing the product of an infinite number of quantities, and he had shown that this product was equal to pi upon 2. So if you divide the 2 down, you get pi upon 4. Turn it upside down, and Bruckner showed you could rewrite it in this form here. Wallis was the first person to use the term continued fraction. Previously, he had used this in a number of his analyses of products and series. So Wallis, a very great mathematician, a difficult man, as everybody seemed to be at that time, but not to worry. Rather later, one sees some other rather sort of elegant examples, which I'll just flash before you. Euler, who knew most of the things that there was to know using the mathematical methods of the time, produced a rather interesting formula which you can arrive at by brute force or a bit of insight bit by bit, that if you have a collection of quantities and you add together products with an extra 1 multiplied each time, so A0 plus A01 plus A01 A2 and so on forever up to the nth term, you can, by just taking factors out and dividing down, rewrite this as a continued fraction. It looks rather messy. You don't really need to follow the n's and the a's. The key point was that he realized that, that you could pick this series here to correspond perhaps to a series expansion of some function like a logarithm or an exponential or a sine or a cosine. And then he would immediately have a new way of representing that function by one of these continued function or continued fraction expansions. A particularly clever one here for the logarithm of 1 plus z over 1 minus z, if you use z as a complex number, the square root of minus 1, then this logarithm is the square root of minus 1 times pi upon 2, and that gives you this wonderful expression for pi as a continued fraction involving squares. So that's just a snapshot of some of the clever things that you can do with this way of representing functions as well as numbers. The reason mathematicians were interested in them at that time, and still are, there are whole branches of mathematics that study these types of representations of very complicated mathematical objects, is that these staircase representations converge very quickly, much more quickly than power series approximations to functions. And so this is a powerful method of approximating very complicated objects by a small number of simple series. Well, we want to avoid the typesetter's nightmare from now on. So when we write this type of staircase quantity that we're going to be interested in, the notation that mathematicians use is to get rid of all these steps and to write this as this little bracketed line. Usually put a semicolon after the first expression here to indicate that it's outside the fractions, and then all the others here just sit one after the other. The way you work out one of these things is really fairly straightforward. Suppose you were to start with pi, then the first entry is the whole number part of pi, that will be 3. And to get the next one, you just take 1 over what's left, 0.14, etc., and then take the whole number part of that quantity, and that gives you the second entry. What's left from that whole number part, turn that upside down, take its whole number part, that gives you the third one, and so on. So we'll look at that again a little later. If you have a rational number, so a fraction, a ratio of two integers, then its continued fraction expansion will come to an end. It will be finite. Obviously, simple fractions like a half or a third are essentially their own continued fraction expansions. If you have a number like a half, then you can always write it in two ways. You can write it as 0, 1 over 2, but you could also write that 2 as 1 plus 1 over 1. So there's this odd little ambiguity. You could always write a half as 0, 2 or as 0, 1, 1, because 1 plus 1 is 2. The convention is that you always take the shorter one, so you don't use this artificially one step longer one. Rather more interesting, we'll spend more time looking at them. Irrational numbers, like pi, like e, like the square root of pi, the square root of 2, they have a unique continued fraction expansion, and it's infinite. So there's a clear distinction between rational and irrational numbers, just in whether the continued fraction expansion is finite or whether it's infinite. Let's look at a few famous examples. Having said I won't use a staircase, I'll just show it one more time. Pi we introduced, always a nice number to think about. Here's the continued fraction expansion of pi. down to some dozen or so places. And here's what it looks like if you lay it out. If you keep going with this, it just seems to be higgledy-piggledy, a bit like the decimal expansion of pi. There's no magic formula that seems to capture what's coming in this, although we'll see later on there is a structure of a probabilistic sort. Most of the entries are rather small, but occasionally there's a rather big one, like this one here. On the other hand, if we take a number like e, 2.718, the base of the natural logarithm, as Coates, contemporary of Newton in 1714, edited the last edition of the Principia for Newton, showed that if you take e's continued fraction expansion, it's totally predictable and has a remarkable pattern to it. So the integer part is 2, that's the first bit. If you invert 0.718, okay, the integer part is 1, so on. So it goes 1, 2, 1, 1, 4, 1, 1, 6, 1, 1, 8, 1, 1, 10. So it marches forward with 2 1s followed by the next even number. So in some sense, pi is more transcendental, it's more irrational than e when looked at in this way. We've seen that the golden ratio has this very predictable continued fraction expansion. And there are other numbers which do other complicated things for a while, and then they end up having all their continued fraction expansion entries equal to 1 ever afterwards, all the way to infinity. Those numbers are called noble numbers, conventionally. Okay, so they end with an infinite sequence of 1s. And we'll see a little later why they can be rather important. In some sense, these numbers are, or the golden ratio here in particular, they are the most irrational numbers. They are the farthest away from rational numbers. And that has all sorts of physical consequences in astronomy and in physics. If you take the square roots of whole numbers, then you find that the continued fraction expansions repeat. You may have to go longer and longer, and you may have a larger and larger block of integers that take part in the periodic repetition, but eventually they will all repeat. The square root of 2 is particularly simple. Everything repeats, it's just 2's. Square root of 3, it goes 1, 2, 1, 2, 1, 2. So you're already seeing that if you had looked at fractions or you had looked at decimal expansions of quantities like root 2 and root 3 and e, you would have had no suspicion that there was anything particularly special or unusual about those numbers. But we're beginning to see that when we look in this way, all sorts of remarkable hidden structure comes to light. So this is the key reason why mathematicians are so interested in this type of representation. Pi, okay, stubbornly looks rather different. Here is a plot of the size of the continued fraction entries that appear. If you go further and further, this is the number of steps down the staircase. So most of them are rather small. Here, sort of 1, okay, it will be here, here's 2, and you can see there's a fairly wild and odd pattern. There's no obvious structure to it. But what are you going to do with these representations of numbers? Well, you can see that if you take a number like pi, which has got an infinite continued fraction expansion, you could decide, when you got a bit fed up with it, okay, that you were going to stop it somewhere and tidy the fraction up, and what you would get would be a rational number, one number divided by another. And these tidyings up of the continued fraction, cutting it off at some stage, are known as the partial fractions or the rational approximations for the number in question. So let's look at what happens with pi. And we label these usually as p over q, so pn over qn, so the first one, p1 over q1. So if we stopped after 3, we would have just P1 was 3. It's interesting, I was looking at the old records of Mr. Bruckner at the Royal Society. I think one of his main events of him being inaugurated as President of the Royal Society, introduces Pepys to the Royal Society and commends Samuel Pepys to the Fellows. And Pepys gives a lecture about mathematics and mentions some of these matters of continued fractions and pi. And somebody objected from the floor that Pepys's mathematics was heresy, because in the Bible, in the book of Chronicles, I think it says rather clearly that pi is equal to 3, because a circle is described as having a particular circumference and a diameter which is just 1/3 of that amount. Therefore, pi must be equal to 3. Well, Bruckner sort of took this up and I think really hinted that you should really just be looking there at the first approximant to pi, that this wasn't a damning indictment of the mathematics of the chronicler. Well, suppose we go to the next step here, okay? We just take the next step down the staircase in the fraction and tidy it up. What do we get? We get 3 plus 1/7. 22/7, you probably remember that from school. This was the rational approximation to pi that you were generally fed to use for your problems and so forth. This is where it comes from. It's the first approximant from the continued fraction expansion. If we went one step further, so the next digit is 15, we get a much better approximate, 333/106. The next one is 1, it's not much better. This enormous number here gives a very, very fine approximation to pi, with 5 digits on the top, on the bottom, and 6 on the top. And so it goes on. So these approximants get better and better as approximations to pi. And you can see that if you specify some level of accuracy that you require, then you can just keep going, cutting off the staircase where you require to get a better and better rational approximation to pi. Well, what you see here, clearly demonstrated by this number here, is that the secret for getting a good approximation out of a small number of terms is for a very large number to appear early on in the expansion of the continued fraction. So let's just compare what's happening here with decimals. Suppose you take the decimal expansion of pi up to 4 decimal places, 3.1415, okay? So if you cut that off at that point, you would be getting an approximation to pi that looked like that, or if you cut at 2 places, like that. Here's the continued fraction approximation, cut at the same number of places. They look almost the same. In the denominators are not very different, but the error in the decimal representation is about 19 times bigger than what you get from the continued fraction expansion. If you go a bit further, okay, and take some more terms, okay, then you're doing 100 times better than you would with 4 decimal places just taken from the decimal expansion of pi. So this is the general state of affairs. If you use continued fraction expansions, you do much better than decimals. Well, one rather legendary mathematician who knew an awful lot about continued fractions, from trial and error and experience and his extraordinary memory, is the great natural Indian mathematician Ramanujan. And if you look at many of the extraordinary formulae that he supplied Hardy and Littlewood in Cambridge, that they spent many, many months trying to understand and figure out how he had invented these formulae and identities, you find a few simple ones as well as some very complicated ones that reveal that he had a very, very good working knowledge of continued fractions. One of the most complicated, which I haven't shown here, is a series representation for pi, the first term of which gives you an approximation that's good to about 1 million places of decimals. Here's a very simple one. And when you see it, not knowing about continued fractions, you wonder how he did it. That if you write pi as 2143 over 22 and take the quarter power, then this rational approximation is good to 3 parts in 10,000. So that's rather extraordinary. How would he do that? How would he think of that? Well, I bet that he knew by heart that the continued fraction expansion of pi to the fourth looks like 97, then 2231, and then there is a fantastically large number appearing, 16,539. So he knows if he chops this off here, he gets a rational approximation for pi to the fourth, which is actually 2143 over 22. So that when he takes the quarter power, he gets this extraordinary good approximation to pi. If you're very patient, the 431st digit of the expansion of pi is bigger than 20,000. Another thing that Ramanujan liked to do was to generalize the idea of continued fractions to continued functions. So instead of having a nested series of fractions, he challenged in a magazine article for people to evaluate this nested sequence of square roots that went on forever. And then in the solution, he revealed rather remarkably that there is a formula that x plus 1 is equal to this nested sequence for any x you care to choose. So he had chosen the example here where x was equal to 2. Well, these approximants start to lead us towards some remarkable features of the behaviour of continued fractions. So we've seen that if we follow those approximants, those rational numbers that approximate an irrational number, that they get better and better as you include more and more terms in the continued fraction expansion. And in fact, there's a simple measure of how good the approximation is, that if you have an approximation like this, then the difference between the number and the approximation is always less than the square of the denominator here, 1 over the square of the denominator. So if you were using 22 over 7 as your approximation for pi, it will be 1 over 7 squared, 1 over 49. And if you kept going for those very, very large denominators, this gets very good very quickly. Mathematicians in the early 20th century went on to ask a slightly different question. What's the best possible approximation that you can get out of this? Okay, so, and that turned to be just slightly different. This wasn't the best possible. It was always true. But if you introduce a root 5, so 1 over q squared root 5 is the best rational approximation that you can get in the limit of an arbitrarily large number of terms. And what's interesting about that is that if you look back at our golden ratio, that was the number with all the ones in the continued fraction expansion, that is the irrational number that keeps farthest away from rational approximations always. So it's the hardest number to approximate in this way, and you have to go further and further downstream to do as well as you might like with a number like pi. So, roughly speaking, at each stage, the distance between the golden ratio and its rational approximant is about 1 over q squared root 5. So it always hovers just on that boundary of the worst possible case. So this is the basis for the statement that I made earlier, that this is the most irrational of numbers. It's the number which is farthest away from rationals in this rather well-defined sense. It's not quite unique in this respect. If you made a new number, which was some linear combination of it, and divide it by another linear combination such that these constants, a, b, c, and d, obey the simple formula, then the same thing is true for that number. Well, what can you do with this sort of representation of things? it's very useful in many situations to be able to produce quick and easy approximations using rational numbers. And a famous example is creating gears and ratios of gear sizes. So if you have two cogs, like the picture on the bottom, then the ratio of the number of teeth on each of the two cogs governs the relative speeds with which they will move when they mesh together and rotate. So if you have a 10-tooth gear here meshed into a 50-tooth, then the 10-tooth is going to go 5 times quicker, it's going to go in the opposite direction, to the 50-tooth gear. But suppose someone comes along and says, well, for our super machinery here, we want the smaller one to rotate the square root of 2 times faster than the bigger one. Okay. For geometrical reasons, this is the sort of requirement that you might have. And you can see you might have more than one requirement if you want to mesh together many, many different gears. This could be part of a much more complicated problem. Well, there's no number that would do this exactly, because the square root of 2 cannot be written as the ratio of one whole number divided by another. That's why it is an irrational number. So what we're interested in is how close can a rational get to the square root of 2? And that's going to tell us our best possible gear ratio. So if we look at the continued fraction expansion of the square root of 2, I think I put it in one of the slides just back there. It was rather simple. It was the one that had the 1 and then all the 2's. They look like 3 halves. Remember, the actual value is something like 1.414. Okay, it's the first part of the decimal. 7/5, 17/12, 41/29, 99/70. They're getting better and better. So what would this mean if you were an engineer? Well, if you went for one of the simple approximations, 1 2/5, so that's 1.4. Okay, it's good to 1%. It's quite good. How would you do it? You would have to have 7 teeth on one gear and 5 on the other. That's not very practical if you're the maker of gears. Okay, they're not going to mesh very well if you've got so few. So why not turn 7 over 5 into 70 over 50? So in that case, you would be putting 70 teeth on one gear and 50 on the other. If you wanted to do much better, you could move up to this one. You could have 99 on one gear and 70 on the other, and the error would be very, very small, 0.007%. So you can see how you can set about engineering according to your requirements. You know, you might only be able to make a gear that has 80 teeth on, so you wouldn't be able to go to 99. The first use of this, rather spectacular and interesting one, was to make these little scale models of the solar system, sometimes called orreries. You can see them selling for enormous sums of money in the window of Phillips's shop in Jermyn Street, near the Royal Astronomical Society, if you want to go and see them. I think those shops think that fellows of the Royal Astronomical Society are in the business of spending millions of pounds on these devices. Alas, they're not. But these are called orreries, incidentally, for an interesting reason. A gentleman, Mr. Graham, was the sort of house astronomer of the Earl of Orrery in Ireland many hundreds of years ago. And the way science was done at that time, you hired your own astronomer to do astronomy for you and look after your observatory if you were a wealthy family. And Graham built the first model working mechanical solar system, and he called it an orrery in honour of his patron, the Earl of Orrery. Well, the first person who set about systematically understanding the mechanics of the gears of these objects was the great Dutch mathematical physicist Christian Huygens. And in 1682, he wanted to figure out how he could make a proper scale model of the solar system. And his first challenge was to deal, for example, with the orbit of Saturn. So Saturn's orbit At the time he believed it was 29.46 years was the time it took to orbit the Sun, and the Earth taking 1 year, of course. And so he wanted to know how should he construct his gears. Nowadays we know it's closer to 29.43. But let's stick with 29.46, which is what he did. So he calculated that he needed his gears to have P teeth and Q teeth, where P over Q was as close to 29.46 as he could make it. And he knew that he needed to have P and Q really between some reasonable values if he was going to be able to machine the teeth. And he picked between about 20 and 220, I think. So what he's got to do is to find the continued fraction expansion of 29.46. And if you do that, the first few rational approximations, the first one is just the whole number part, 29. The next one is the whole number part of 1 divided by 0.46, 59 over 2, 206 over 7, and so on. So what he did, this case, was to build one gear with 7 teeth and the other with 206. Okay, so that was the fraction which stayed within his requirement. If he went to another one, better approximation, but too many teeth to be cut. So this is how he dealt with one particular planet. You can see you then just move on to the others and build up the whole mechanism. So the next time you're building your orrery at home, remember continued fractions are what you need. The next part of our story changes tack. We're going to start looking at the continued fraction expansions of irrational numbers, and we will find that there are remarkable patterns in them if we look in the right way. And the right way was first noticed by Gauss, and it involves thinking using probability. Gauss is generally acknowledged by mathematicians to be the greatest mathematician of modern times. Here's a picture of him in old age. Here's his rather beautiful signature. You can see you have to have a lot of time on your hands to sign your checks with that. But it's not so easy to forge. Gauss was good at absolutely everything: pure maths, applied maths, the Gaussian distribution of probability, complex numbers, number theory. All these things are invented by him all over mathematics. There are things that bear Gauss's name. And in later life he became interested in electromagnetism, and you probably know that the units of magnetic field are named after him. He made important contributions there. He was the first person to develop the theory of errors and least squares, which he did in order to predict where an asteroid would appear after it came out from the shadow of the Sun, when the data describing its motion was incomplete. So he could work out what was the most likely place where it would appear, and he was correct. He was a formidable mental calculator, and on one occasion there's a story of how another mathematician asked him how he managed to do all these calculations so quickly and so precisely for some enormous set of tables and predicted astronomical motions, and he said, "I use logarithms." And the questioner said, "Oh, yes, but don't you find it just takes an awfully long time to keep looking them up and so forth?" He says, "Oh, I didn't look them up. I calculate them in my head." Well, what's probability got to do with continued fractions? One of the things that we've seen is that if we have some list of integers, okay, and we put them in that staircase, okay, so they go on forever, they will uniquely specify some irrational number. And if we look in the other way round, if we have an irrational number, it produces a unique staircase of numbers by its continued fraction expansion. So any infinite list of numbers produces one and only one continued fraction expansion, and that corresponds to one irrational number. So what the message you should take from this is that there actually can't be a general theory of the frequency distribution of numbers for every continued fraction expansion, because any list of numbers you care to give me produces some number, some irrational number, by its continued fraction expansion. But the extraordinary thing is that if you modify your language and say, what happens to the continued fraction expansion of almost every number, and by that, mathematicians can define that rather precisely, it's just like there's an isolated collection, a list of exceptional numbers. E is one of them, we've seen already. Then if we exclude those, then all the rest obey some general pattern that can be defined by probability. So what we find, and this was inspired by Gauss's work in the 19th century, that if we study the continued fraction expansions of numbers which continue indefinitely, the continued fraction expansions continue indefinitely, then the probability that the digit k appears in that continued fraction expansion is given by this formula. So it depends on the natural logarithm of 1 plus 1 over k times k plus 2, and then the whole thing is divided by the natural logarithm of 2, which is 0.69. There are two things to notice about this formula. So if we want to work out what's the probability that 1 appears, if you've got a good memory, you may remember that 1 had been appearing rather a lot in the numbers that we saw, and occasionally we dwelt on the fact that a very large number appeared, like 292, and that was clearly rather exceptional. Well, 41% of the numbers, so p is 0.41 when k is 1. 41% of the entries are just ones for almost any number. 17% are 2s, 9% are 3s, 6% are 4s, 4% are 5s. Almost everything is loaded down in these very small numbers. If we say, what does this formula look like when k becomes large? Well, when k is really large, k plus 2 looks like k. This is 1 plus 1 over k squared. We can expand that as a logarithm. 1 plus 1 over k squared looks like 1 over k squared. So when k is very large, this probability looks like 1 over k squared. So to have a very large entry like 292 in pi, you can see it's 1 over 292 squared. It's very, very slight probability. 1 part in 10 to the 5, 1 in 10 to the 6. So this formula gives you a feel for what these continued fraction expansions typically look like. And if we were to look at the frequency distribution for the digits in pi, for example, we find that they follow this pattern really very nicely indeed. Let's just look at that formula a little more closely. You could ask, well, OK, you're telling me what the probability is, but what's the average? You know, what does the typical entry look like? So what's the average entry? Well, that's rather awkward. The ordinary average, which we tend to call the arithmetic mean, OK, you just get by working out the sum of k times p over k. Well, when k gets large, we've just seen p over k looks like 1 over k squared, and so this looks like the sum of 1 over k. So 1 plus a half plus a third plus a quarter and so on. And this is a famous series. We've seen it before in lectures I gave last year, sometimes called the harmonic series, 1 plus a half plus a third plus a quarter and so on forever. And it's easy to see that the sum is infinite. This series doesn't diverge, and you don't have to do any calculation. You just have to underline things. So take these two terms, and then take the next 4 terms, and then take the next 8 terms. Well, this sum here, a half plus a third, okay, those terms are both bigger than a quarter. And these terms here are all bigger than an eighth. And these terms here are all bigger than a 16th. So the sum of this series is bigger than a half, plus 2 quarters, plus 4 eighths, plus 8 sixteenths. These are all halves. So the sum of this series is as big as as many halves as you want to add together forever. And that number is infinite. So this series here, unfortunately, diverges. So there is no answer to the question, what's the average entry in the continued fraction expansion? Although 41% of the entries are ones, the tail off is too slow to make the likelihood of very, very large numbers appearing occasionally to be vanishingly small. But nicely, there's another mean, which we also come across last year. Remember, we once talked about the geometric mean and retail price indices. So if you want to combine lots of quantities that have got different units, the geometric mean is the one you want to use. And what the geometric mean of a list of quantities k1 to kn is, the arithmetic mean is just add them together and divide by n. The geometric mean, you multiply them together and take the nth root. So if there's two of them, x and y, you multiply x times y and take the square root. So if one of them was 5 and the other was 5, okay, geometric mean would just be 5. If one of them was 4 and one of them was 9, multiply together, you get 36. You take the square root, you get 6. Okay, whereas the arithmetic mean of 9 and 4, 13 over 2, 6.5. They're slightly different. And the remarkable thing about continued fractions, I'm not going to prove this, it requires quite a lot of effort, although it's not particularly difficult, it's rather complicated. If you take the nth root of the continued fraction entries in the staircase, that as the number becomes increasingly large, so as n goes to infinity, this geometric mean tends to a universal constant, sometimes called Kuzmin's constant or Khinchin's constant. These two people were greatly involved in proving it in the early years of the 20th century. And its value is about 2.68. So this does capture the fact that the mean, the average entry in the staircase is rather small. So its geometric mean somewhere between 2 and 3. You converge rather slowly to this. We'll see some pictures in a moment. If we look at an example like E, remember E is exceptional. It's one of this group of almost every excluded numbers. So it doesn't behave like pi. The entries just keep marching, getting bigger and bigger, 2, 114, 116, 118, and so on forever. If you work out the geometric mean for E, then it grows as n to the third, where n's the number of entries. So that should be a small n. So this is one of the exceptional cases to which the general theory doesn't apply. Here's a picture for pi. It's Mr. Khinchin down here, Khinchin's constant. Here's the geometric mean. Okay, the product of the k's, take the nth root, as the number of k's gets bigger and bigger for pi. And you can see at first it sort of oscillates about a bit, and then gradually it's really converging rather slowly. 2.68 is somewhere around here. It's heading towards it. As it goes on, the oscillations get smaller and smaller. Even Khinchin's constant itself, if you work out its continued fraction expansion, it seems to come to this number. Here's another picture. Same quantity, okay, geometric mean, it's being called n on this picture. And what we're looking at here is E. We've seen that grows like n to the third. That's exceptional. Here's the value of Khinchin's constant, the 2.68 roughly. And here's what happens if you look at root 2, root 3, and the golden ratio. So these are all exceptional quantities which don't approach this universal constant. Here's some that do. Okay, so here's pi again, from the top down. 2 pi, this is the Euler constant, the natural logarithm of 2, cube root of 2 and the cube root of 3. There are many mysteries about this number. I think its irrational properties are not fully understood, and it's not known if there is some general pattern followed by all numbers that approach it in this approximation. If you look at this picture, you might suspect that there is. Okay, these numbers are very different. They're all heading towards 2.618 eventually, and there seem to be oscillations and patterns which, if you just shifted the curves up and down, really look rather similar. So there's a hidden, challenging problem sitting here about these numbers. There's another quantity that had popped up that was universal for almost every number. So if we look at the rational approximation here, so for pi, our 22 over 7 and so on, if we keep going, looking at better and better and better rational approximations, then we can show that the denominator here, although it grows, it doesn't grow arbitrarily fast. There's a limit on how big they can get, and therefore on how good the approximation can ever be. And Paul Levy, who I think was the research supervisor of Bennett Mandelbrot, who died just a few weeks ago, the famous inventor of the term fractals and a good deal of the study of fractals. So he proved that the Q's couldn't diverge faster than the exponential of some particular number times n. And a way of rephrasing that is if you take the nth root of Qn, it'll just be e to the a. It'll be some number. And so he proved that the nth root of the Q's approaches a universal constant for the continued fraction expansion of almost every number. So again, there's an extraordinary universality here that you would never have guessed. Just as with Khinchin constant, for almost every number, hidden within the continued fraction expansion is this universal constant, rather the status of something like pi. And this number is about 3.275. It's actually composed of log 2s and exponentials and pi's. And here's a little picture doing it for pi. If you work out the Q's for the fraction expansion of pi, here's a picture of how quickly you're starting to converge to this special number, gone about 800 or 900 continued fraction expansion terms. Again, you can see the convergence is rather slow. This is a little challenge problem that was set that I came across a few years ago and solved. And it was in one of Pickover's books. And he said he got the problem from these two physicists, Pettit, who's in France, and McFedrin, who I think is in Sydney. And it's this strange series. Makes a nice project, I think, for students to work on. So you're looking at the series of 1 over p cubed sine squared p, when p goes from 1 up to some quantity we'll call n. So this is a curious series. So if you put it on your computer and you work out all these terms, you can see 1 over p cubed is getting smaller and smaller and smaller for each term. So what you suspect is that this series must likely converge. And after 22 terms, the sum looks like 4.75, and you keep going, it's still 4.75, and then I'm jumping here. If you go up to 310 terms, it sort of found its way to 4.80, 313, it's 806, so it seems to be converging to 4.806 something. And then when you get to term 355, its sum suddenly jumps up to 29.4. And it continues hovering around 29.4. And so Pickover's challenge was, what happens to this series? Does it converge? Or does its sum become infinite? And the trick to understand it is to think about continued fractions. You see, what happens here is that every so often, 1 over sine squared p becomes quite close to 0. And 1 over 0 produces a very big jump in the sum. So you can ask, well, when does that happen? Well, when p is some whole number times pi, then the sine of a whole number times pi is very close to 0. So whenever p looks like q times pi, then the sine will be close to 0 and the sum gets a big boost. And you could say, well, you would expect that to happen whenever p and q look like a rational approximation to pi. But we know what they are. They're continued fraction expansions. And so what we're saying is that when the term in the series p satisfies this relation, we expect a big jump in the sum. So we just have to read off the numerators. And indeed, 355. 333 gives a big boost as well. If he kept going to term 103,993, he'd find an even bigger boost. So these highlighted yellow terms in the continued fraction expansions are where you're going to get a big addition to the sum. And they continue forever, and their boost gets better and better. And we know from what Levy has told us that they actually grow exponentially. They outweigh the effect of the 1 over p cubed. So this series diverges. Well, the last thing I want to show you is something about chaos in numbers. If we generate the continued fraction expansion of a number, then let's suppose we write that number as a whole number plus a fractional part. A notation that we use if the number is u, we put a square bracket around the u to represent the whole number part. So for pi it would be 3 plus this part. Here's the second digit is 7, the third is 15. So we've seen this already several occasions. What's interesting about this process of generating these digits, one after the other, and the fractions, is that it's chaotic in the sense that we become familiar with in mathematics and physics. That if we make a tiny change in this starting number of pi, if we just change one of the decimal places, then after several applications of this procedure, we will produce a completely different sequence of numbers. So the generation of a continued fraction expansion of a number is a chaotic process. And the process that Gauss found back in 1812, he said he'd been thinking about this curious problem for many, many years. It's this little transformation that you start with a number, call it xn, you derive the next one by working out 1 over xn, and then taking away the whole number part of 1 over xn. And you keep doing that. And that generates the fractional pieces of the continued fraction expansion. And what Gauss was able to show is that there is a simple probability distribution of the outcomes of the x's that just looks like 1 over 1 plus x. And the error is rather small. It gets smaller and smaller with each iteration. The graph of this function is rather strange. It's got an infinite number of pieces, so it looks like 1 over x minus a constant, but it goes on forever. And if you just move very slightly from one curve to another down here, you'll end up being thrown in a very, very different place. So what's the sensitivity to chaos? If you have two very neighbouring numbers, then after you've looked for n steps for the continued fraction expansion, they will differ by this exponential quantity, where this quantity here is essentially Levet's constant times the number of steps. Let's call it t. So continued fractions have this chaotically unpredictable behaviour if you round off errors or you slightly change their behaviour. And my interest in all this many years ago, I'll show you on the last two slides, was in the study of a particular type of universe, a solution that's possible from Einstein's equations of general relativity, which describes one of these universes that starts expanding from a Big Bang and then eventually collapses back to a big crunch. But it does so in a chaotic fashion, because all the different radii in three different directions rather, behave in very different ways. So they oscillate in a complicated way as you head towards the beginning, and then again as you head towards the end. And here's a sort of snapshot picture of what they do, picking a funny time coordinate where we're looking towards the end or towards the Big Bang. So a sort of crunch sits at infinity down here. And what happens is that two directions just wobble around for a while, the third one collapses, then they sort of change places with two of them, and we have a bit of wobbling again, and then the other axis changes places and the other two wobble. And to understand what happened in this universe, it turned out that what was going on was described exactly by continued fractions. That if you set the starting condition by choosing a number, let's suppose we're 6.022987 as it were, the number of little oscillations here in the first cycle was its whole number part, 6. And then the new value for the next cycle was the reciprocal of the fractional part that's left over, which is 43.5. So you had 43 oscillations in the next cycle. The bit left over was 0.53503. Number of oscillations in the next section was 1. Number of oscillations in the one after that, 1, 72, 1, 5. So the whole complex dynamics of this chaotic evolving universe were just determined by working out the continued fraction expansion of the numbers that determine the starting condition. And this turned out to be something that you find in many areas of physics and astronomy, that whenever you have a situation that's chaotically unpredictable in detail, the average behavior is closely linked to the behavior of continued fractions. Continued fractions describe situations which are rather like balls bouncing around off the walls of a closed container. If the walls have the appropriate shape, then two trajectories that are very similar, we rebound in very different ways, and the subsequent behavior is chaotically sensitive to what that starting trajectory should be. So in many areas of physics and astronomy, continued fractions play a key role in understanding chaotic, periodic, and ordered behavior. Our noble numbers that we looked at before, with all the ones in their continued fraction expansion, are the ones that are least susceptible to being made into chaotic behavior. So if you have a system of stars moving with frequencies that have continued fraction expansions which are noble numbers, they are the least susceptible to being shifted away to produce chaotically unpredictable behavior. And the long-term stability of our solar system is linked to the fact that there are many characteristic frequencies of motions which are close to numbers with continued fraction expansions which are noble. So I hope that's given you some survey of fractions and why both mathematicians and physicists are interested in these unusual expansions of numbers in which so much information is hidden away with unsuspected regularities and patterns. Thank you.